Okay, there are many ways to pair data, and if you can do this, it gets rid of some of the variance and gives you more statistical power. It's a good idea. In many cases, I have another video, for example, from the same chapter where the data were just clearly not paired, even though there were 15 data points in the control and 15 in the treatment. There wasn't really a natural way to pair them. Here, we have the same 12 workers doing two processes. So for example, this 87 can pair with this 59 because they're both being done by the same worker. Another case is a pre-test, post-test, before you do some kind of treatment, and whatever your pre-test is will connect with whatever your post-test is. So the advantage of pairing this data is we take these two data sets and then we boil them down to a single data set. Once we do that, we can totally get rid of the original data and just focus on what the difference is. So this subtracts out the individual variation and just gives us more statistical power. So let's take a look here. Our null and alternative, really now we just have a single sample. Even though we have two samples of data, since we subtract and get the difference, this is the only data set we're working with, and it's essentially a one sample test when you can do these pairings, when it makes sense to pair every data point with another data point in the sample. And in that case, your null hypothesis, which should always have an equal sign in it, right? Not like how I did that. Let's do this one. There we go. So the way we call this usually is mu d, and what's that is the average difference. So we're talking about our difference scores down here, which are just subtraction of the two, and the average difference score would be 0. This means that whatever that process 1 is, the average of that is whatever this process 2 is. There's nothing going on, nothing interesting. The alternative would be, let's take a look. So we're not going to use that equal sign anymore. And the question is, can we conclude that the mean assembly times for the two processes differ? So it doesn't say in which direction, it just says differ in either direction. So we can use this not equals sign there. And this means we're doing a two-tailed test, by the way. So one sample, two sample, that's completely different than one-tailed, two-tailed. One sample was the type of tests we were doing in Chapter 8. Two sample was the type of tests we're doing here. But what we did here is we boiled our two samples down into a one sample test. The alternative hypothesis, which is a completely separate issue, tells us that we can reject in either tail. So this is a two-tailed test. Do we use Z or T? Well, it all depends on if we have the population standard deviation. And here we're not given that anywhere. So all we have is our sample stuff to work with, which means we're going to have to do a t-test. Degrees of freedom, I mean, you can think of it as we're really just doing a test on the difference score, a single test. So we have 12 sample points, and our degrees of freedom would be 1 less than sample size. So that would be 11. Value of the test statistic, this formula we saw in another video. We saw the formula here. This is for the Z. Now in our case, we don't have sigma. We don't have the population standard deviation. But what we can calculate is sample standard deviation. So we have a very similar formula that goes like this. We'll take the difference of our sample means again. And then here, we are just doing a one sample test. We are doing a match sample. So in this case, it's even easier. We take the mean difference. So maybe we put like this, minus the null hypothesis difference, which is just going to be 0, by the way, all over, and since we don't have the sigma, we'll just have to work with the sample standard deviation. So this is what we have right here. We have our sample mean minus, this is going to be 0, and then our sample standard deviation divided by our square root of a sample size. So how do we get those numbers? Well, we can just open up our calculator here. Oops, clear that. And let's get our sample mean first. So mean of the difference, that gives us 13.25. So this sample mean right here is 13.25, and I already said that was minus 0, so we're just going to divide that here. And then our sample standard deviation, we can do something similar on the calculator. We just get our sample standard deviation button and send the difference to our calculator, press enter, and you can see here we get 12.850, and we'll put that in here. 12.850, all divided by the square root of our sample size, which is 12. So this is going to give us our t statistic. So let's go ahead and do that on our calculator. So we'll do 13.25 minus that 12.850, or sorry, not minus 0, if we want to do that, and then we can put this in parentheses. You don't really need the 0 there. And then here on the bottom, we're going to have another little fraction. So that's going to be our 12.850 divided by square root of 12. Okay, and this gives us 3.572, and that's our t statistic. Our critical values at the 0.10 level of significance. So what's going on there? This is a little tricky, so let's take a look at this picture here. So we have our distribution, and they said alpha is 0.10. That's the area out in the tails, but because we're conducting a two-tailed test, that means we can reject either here or here. That gives us 5% down here and 5% down here. And the question is asking us, what are these two values? What are the t values that'll put 5% into our tails so that we get a total of 10% here? Well, to get that, we use our calculator here. Let's do that. So we want 0.05 out in the right tail, and we already said we had 11 degrees of freedom. So this is our critical value. This is going to be the positive one. So 1.796. So what's the negative version? It's just symmetrical. So this is going to be negative 1.796. And can we conclude that they differ? So our test statistic was 3.572. So we were, this is t equals 1.796. We're 3 point something. We're way out here. We're well into the rejection region. We're further out in the tail. This could also be if we were a strong negative number, if we were below negative 1.796, but we happen to be over here. And so we are in the rejection region. We do reject. It's statistically significant. Reject the null. We can conclude that the two processes differ because we're rejecting the null that they don't differ. And we can check all of that.